Hey, Calc students, this is Mr. Beck. Today we're going to be talking about the last topic for the semester. The topics that I'm going to be going into are 7.2 integration by parts and 7.5 partial fractions. These two integration techniques are pretty essential in what we're going to be doing for the future. At the same time, these kind of naturally go along with what we did in chapter 4. They're separated in the book, but they're not really separated either on the College Board site or really in the units. So without further ado, just a quick recap on all the different integration that we've done. We've integrated pretty much like integration is the reverse of the derivative rules. So the power rule, we're able to integrate that, and that's the very first set of integration that we did. We had our basic trig derivatives, which we integrated, such as the derivative of tangent is secant squared, so we integrated secant squared. Then we did different techniques of u substitution, and then we had a logarithmic integration, where we had the 1 over u du, which integrated into the natural log of the absolute value. We're going to see some of that again today. Then we did some inverse trigonometry. And now we're going to be doing the last major rule from derivatives that involves the product rule. Now, if you remember in derivatives, we had product and quotient rule. The quotient rule is really a combination of the product rule and the chain rule. So when it comes to those two together into the quotient rule, we don't really have to undo the quotient rule. The only one that we have to undo is the product rule. So if you take a look, and let me go ahead and erase these two really quickly. If we take a look at the product rule, our product rule is listed like this. Well, what happens if we want to actually integrate both sides? If we integrate the derivative, it undoes itself, so we get uv. If we integrate each one of these separately, the integral of u dv plus the integral of v du, and then do some creative rearranging, we get an expression that looks like this. The integral of u dv is uv minus the integral of v du. And that is exactly the way that we typically present integration by parts. It's written that way. The integral of u dv is uv minus the integral of v du. Now, u and v represent actual functions. So how we use integration by parts, what we do is we establish, okay, within an integral, such as the natural log of x, in the integral, we have two factors. One factor is, in this case, is natural log of x. The other factor is the differential of x. So this is natural log of x times the differential of x. One of these needs to be a function which we're going to differentiate. That's what we're going to call u. The other one is going to be a derivative, which we're going to have to integrate, and that is going to be the dx. So if u is the natural log of x and dv equals dx, when I look at my my integration by parts rule, or really the reverse of the derivative or reverse of the product rule, we need to know u, v, and we also have to know du. So once we know u, we find du. Once we know dv, we find v. So really, let me show you that. So once we know u, we're going to have to use it to find du. Once we know dv, we're going to have to use it to find v. And then everything is just going to be putting it into the rule. It's not, I wish there was a more intuitive way of saying, hey, just use the formula, but in many ways it is just use the formula. We showed you how the derivative rule actually worked. That was way back in chapter 2. Now we're talking about just going the reverse. We don't necessarily need to go into the mechanics of it, but anyway, so every time that I write out an integration by parts problem, what I do is I write down the rule right from the beginning until it becomes fairly natural to me. So the integral of u dv is uv minus the integral of v and du I already have multiplied here together. And x over x is 1, so the integral of 1 is, the integral of 1 dx is just x. Now, a lot of times you will see this written as x times natural log of x minus 1 plus c. You are welcome to keep it unfactored. You're welcome to factor it. Both answers are really going to be important for us. So, second problem is what happens when we have a definite integral with an integration by parts problem. So, like before, what we need to establish is we have our u, which we're going to differentiate, and we have our dv. Now these problems are kind of easy because there's really no other option of what we can do, or if there is another option, it doesn't really help us. And I'll explain what I mean later by that one. So If u is the arctangent of x, yes, we need to know du, which is 1 over 1 plus x squared. Dx is dv, so v is x. So once again, integral of u dv, so the integral of arctangent, is uv minus the integral of v du. Now, once we have our uv, which in this case is x times the arctangent of x, one of the things we must keep in mind is we have taken the definite integral, so we need to include the limits right here. So uv minus the integral of v, and then du is the 1 over x squared. Now, if you notice in red, what I've done is I've multiplied by 2 and multiplied by 1/2 so that I could do the mental u substitution. One thing that I do caution you on is if you have to still do the u substitution, then what would happen is this is the integral, so we would say u equals 1 plus x squared, 1 plus x squared. So du is 2x dx, which is why I put in the 2 and compensate with the 1/2. This is now the definite integral from 1 to 2 of 1 over u du. So you have to make sure you maintain your limits, which is why I've been strongly encouraging all of my students to try to take that approach of you already understand where the u substitution is going. So understand this is a 1 over u du problem. And that way you can just directly integrate it into the natural log of the denominator. So that way also, if you notice, I have all of this as a definite integral from 0 to 1. And 1 times the arctangent of 1 minus 1/2 times the natural log of 2 gives me the pi over 4 minus 1/2 natural log of 2. 0 times the arctangent of 0 is 0, and the natural log of 1 is 0. So that's where those are just 0. We get our answer of pi over 4 minus 1/2 natural log of 2. A lot of students always ask, well, should we make that the natural log of the square root of 2? Yes, you absolutely can do that if you need to. But it comes down to you need to be prepared to see the answer you have based off of what the answers are given in a multiple choice section and work with it from there. So big thing that we need to focus on is what's the difference between the indefinite integral and the definite integral. When you do the definite integral, make sure that you use the limits from 0 to 1 in this case, or if you do want to do a u substitution, make sure you still change your limits. This is where it gets fun on one level, but at the same time, you have to pay very, very close attention to your notation. So as we do the next problem, if you notice, I actually did this problem in 2 different ways. The first way I did wrong, and I intentionally did wrong, and I actually left that on my notes intentionally. The reason is because a lot of this is problem solving. How do you know what approach to actually take to begin the problem? So if I had said, okay, now I have 2 distinct factors, really x and e to the x, so 2 distinct functions that I need to know what to take the integral of. What do I establish as u? What do I establish as du? If I had said u equals e to the x, well, du is actually a very nice e to the x dx, but then dv would have been x dx, so dv would have been x dx. So v is 1/2 x squared. So what ends up happening when I use my integration by parts, I end up with this integral that results. And again, the reason why I left this on here and I had it crossed out is because I want to say, well, what occurred? I now went from one integral to an integral that is incredibly harder. So with that in mind, it's like, okay, that's the wrong approach. So how do we know what approach to take? And what I'll say is E is kind of the indication. E is the indication because E is a very, very flexible function. You can differentiate and you can integrate and both end up being e to the x. And so because of that, it's very, very fluid and very, very workable. Meanwhile, what ended up happening here? We had an x squared in the integral that we now have to evaluate. So that polynomial actually went up a power instead of down a power. So that's the key, that if we have a polynomial along with e to the x, or if we have a polynomial along with one of those other functions, that polynomial must be differentiated down so that we can get rid of that. So that's what I did. U equals x, so du is dx, dv is e to the x dx, and v is e to the x. So if I use my integration by parts, uv minus the integral of v du, now I have a very nice integral to work with. So once again, if you have a polynomial and you have a function, whether it's e or whether it's like a sine or cosine, you really want sine or cosine to be the derivative, because those aren't ever going to go away when you differentiate them. Polynomials will. Example number 4, honestly, is very, very similar to example number 3. The key difference is this is where we have a quotient. So I would turn it into the product by making it e to the negative x. And then a lot of this is straightforward. So u dv is ub minus the integral of v du. Only thing, be careful of, make sure that you account for the chain of that e to the negative x. And so now I factored this. Does this problem actually need to be factored? And honestly, no, it does not. Factoring does make it look a little nicer, and it's a lot more fun to work with, or how about a lot more manageable to work with? For instance, if there is no c here, do we have critical numbers? The critical number would be x equals -1. That's if this were a first derivative. So it helps us find the zeros. But basically, factoring is a very, very nice way that we can approach things. But it's not necessary that we have to actually do it that way. So on to example number 5. Once again, now we're mixing a polynomial and we're mixing a rational function. Not rational, radical function. That radical function is 5 plus 4x to the negative 1/2 power. Now, if I differentiate or I integrate it, it's not going to go away. Kind of like what I said about whether it's e to the x or sine of x or cosine of x. If it doesn't go away, it's not a very, very good candidate for it being u. So I set u equal to x, so when I differentiate it, it's just dx. Now the dv, when I integrate it, my mental thought process behind this when I integrate is number 1, I have to raise it to a power 1 above. And then I have to compensate for that 1/2 by multiplying by the reciprocal, which is where that 2 comes from. Now, we also have that 5 plus 4x. This 4, when I take the derivative, that chain shows up. When I integrate it, we have to divide by 4, which is why I wrote this as 2/4. Obviously, 1/2 is a better way of writing it. But don't forget when you're integrating, and notice how I'm doing this without a substitution. But when I'm integrating this, what I'm looking for is what are all the chains that I need to compensate for when I do my integration. So after that, it's pretty straightforward. uv minus the integral of v du. Then integrating that one, once again, raise it to 1 power above, multiply by the reciprocal, and don't forget the chain of that 4. And if you see on here, I actually factored it further. Once again, this is a legitimate answer. I'd be happy with you writing that as an answer, but it's up to you, really up to the situation, whether you need to do something further with that. And that something further would be, doesn't need to be factored so you can evaluate it for different reasons. Example number 6. So example number 6, let me not give away everything too quickly. So on example number 6, what I have here is, okay, remember how I said cosine is going to be the one that's a little bit more flexible to work with, and it doesn't go away if I differentiate it. Now the x squared will. So if I say u equals x squared, dv is cosine of x, uv minus the integral of v du. But what happens here is this is not an immediately nice answer. So this is not an immediately nice answer. As a result, what's going to happen is we are going to have to integrate by parts one more time. If we do this, you notice I have this in pink. If we do this, I need you to write u1 v1 and u2 v2. So by writing it that way, now you can, now we've distinguished that we have, or we're doing this twice, but also distinguish that u is one thing, while v is another thing. So we integrate by parts again. One of the things, if you notice, I said dv was just sine, and so that makes v negative cosine. By doing that, it creates a lot of negatives that we have to compensate for. So one approach that we could take is, what happens if dv was negative sine of x, then v would have been cosine of x, and it actually would have simplified some of those negatives. And don't forget, you have to distribute to that entire second integration by parts that you just did. So, moving right along, sample AP problem. So if we were taking the integral of f of x sine of x, and this is kind of like the way that they would assess this kind of problem, because what you're looking at is what happens when we want to know the formula behind integration by parts, but we don't actually want them to evaluate it. Excuse me. So anyway, if you could see by my work, what I have identified is this is u, this is dv, which makes this v. And so u has to be the 3x squared because this is plus minus negative. Anyway, it's a positive x cubed. So moving right along. This is where I come up with a summary. Now, I don't like saying here's a rule, follow the rule, because if we have a rule and we follow the rule, then it's what happens when the rule gets broken. So what I'm about is let's actually think through this in a reasonable way to say, why should we do what we want to do? So if you noticed these three problems, remember x to the nth. If I have x to the nth and I said e sine or cosine, sine and cosine never go away, but eventually we can get that polynomial down to 0 if we do integration by parts often enough. So we want the polynomial to be u. So u would be the polynomial in a situation like that. Now, what happens when we have natural log? Well, the integral of natural log then is not a very, very pretty thing. We actually did that earlier, x natural log of x minus x, but the integral never actually gets rid of the natural log. We integrated arctangent, and when we did our arctangent, we noticed that we set u equal to the arctangent. Now, the reason for that is because the derivative of natural log of x is 1 over x. The derivative of the arcsine is 1 over the square root of 1 minus x squared. I know I'm ignoring the a's, by the way. And 1 over 1 plus x squared. So by differentiating these, we get these more into the algebraic form as opposed to their transcendental form. But we get these into the algebraic form that we tend to have something to work with. In fact, that 1 over 1 plus x squared, we took the derivative of x. And so by multiplying those, we now had a u substitution approach to the problem. If I end up with an x right here, what I could do is, once again, a u substitution problem. So in cases like that, we actually let u equal to the natural log of x or u equal to the transcendental function because they differentiate into more of an algebraic form. Now, what happens if I have a mixture of both e and sine and cosine? Well, that mixture of e and sine and cosine, to be honest, it really doesn't matter which direction we take. There is a preferred method. Which one is more flexible, e or sine or cosine? And since e is more flexible, what I tend to do is I let e equal to the derivative. So that way I could work with it a lot more flexibly and then let u equal the sine or the cosine. So in the situation that I have here, I'm going to just present this to you in its full form. Yes, I'm still going to talk about it, but I'm presenting it to you in its full form because something special happens in this problem. When we do our integration by parts, like I said, I set my dv equal to the e. I set my u equal to the sine. Going through the integration by parts, I get this expression. Now what I did was I subtracted the negative, making it a positive. I had to do integration by parts again. When I do my integration by parts again, if you follow, I end up with this expression. Now, this is a special type of problem that by integrating by parts a second time, what ended up happening was we created the actual integral. I'm going to change my color into pink. We created the actual integral that I was trying to start with. So a lot of times you'll see that they say, okay, let's let that overall integral equal I. So I, which is the integral we're looking for, will equal some expression and then plus another I, which then we can combine together onto one side. And then to go from here, I multiplied both sides by, let me go ahead and change the back colors. I multiplied both sides by 9/34 to solve for the actual integral that I want. So it's a very special thing that we can do, but sometimes it's essential. And this is what I call, we are not directly integrating, we are doing an indirect integration because we are eventually solving for expression that creates its own self in the problem. So the integral of sine squared. If I have the integral of sine squared, I'm going to take a look, and we've already established what the integrals of each of the individual trig functions were. Doing the natural log integration helped us do tangent, cotangent, secant, and cosecant. Well, we understand the integral of secant squared. So we know that the integral of secant squared, we know that that one's tangent. The integral of tangent squared, we could turn that into the integral of secant squared x minus 1. And so that would end up being tangent minus x. But we can't do, and for that reason, we can now do cosecant squared. We already knew that one. Integral of cosecant squared and the integral of cotangent squared, we can do that. What about the integral of sine squared and cosine squared? If we're trying to do the integral of sine squared or cosine squared, this is one approach. Probably the better way of doing this is by what we call a power reducing formula. But anyway, if you remember those, we're going to talk about them more next semester. But the integral of sine squared, if I break it up into sine times sine, then I could say, okay, u equals sine, dv is also sine. And if we go through our integration by parts, we get uv minus the integral of v du. Now, if you notice, I ended up with a cosine squared as a result here. And if we remember, cosine squared x is 1 minus sine squared x. And by doing that, once again, I get that I equals something, and then with an I associated with it as well. So then I bring the I to the other side and divide by 2, which is where I get this expression. Something I didn't mention, which I should have before. Usually I'm a very big stickler for, okay, as you're going through your integration process, make sure you add C the moment after integration. When it comes to integration by parts, especially if you have to do multiple integration by parts, it tends to get really, really messy. And to avoid that messiness, I will say the moment you do your final integration, make sure you put a plus C at that moment. And then work with all the coefficients at that point. So I don't like doing that, but at the same time, my focus right now is making sure you can do the integration by parts properly and then put the plus C on at the end. If we had to do this and we had to account for all the individual C's, that's where we would do something more with differential equations. And those differential equations, we have the C's for a short amount of time and we work with them more specifically. So as far as all of these go, this is the only case that I say, okay, throw on the plus C at the very end. That's lazy mathematics, but at the same time, right now, there's, if you look at this problem, there is so much going on that I want to make sure you get that and then put the plus C on at the very end. Now, integration by parts has something called the tabular method. The tabular method is just a shorter way of actually writing the whole integration by parts process. What happens is we have u here, and this is our dv. Well, this column, we differentiate until we get to 0, as you can see in the pink there. In this case, we are going to integrate. So we're going to take the integral of all of these. Now, what happens is the integral of, in this case, the sine of 4x is this expression. What this turns into is u times v, because those two are going to be multiplied, minus the integral of v du, which this is the integral of v du, but it's actually the integral of v du written out in its full, like already integrated form. And then we'd have minus a negative, which is why it's a plus, these two multiplied. And so the overall result is going to be this combination of these two multiplied minus these two multiplied plus these two multiplied. So that's what I have here. What I established is with our polynomial here, our polynomial is typically what we want to establish is u, because that's going to go away and eventually become 0. And then the dv is going to be the sine of x dx. Remember, that's the more flexible one. E and sine of x are both really flexible. So the u and then integrate, so differentiate down, integrate all the way up. And so we get the uv minus the integral of v du by those two multiplied, plus those two multiplied, plus those two multiplied, plus these two multiplied, and then put the plus c on at the end. Over to problem number 11, same kind of thing. We're going to have just establish u is going to be the polynomial here. dv is going to be that integral expression. And so we differentiate down, and then we integrate these. And once we integrate those, make sure we account for the change in the sign. So this is plus, minus these, plus these. We can write it out. Now this is a situation that it's probably better to actually do a factoring of this one. Factoring of this one is really, really nasty, because we're going to be factoring out a 1 over 105, as well as the 2x plus 1 to the 3 halves. The nice thing is what's left over is a nice happy quadratic. I didn't actually do it here. It's not essential, but it's a little prettier looking. Now with this problem right here, this integral of x secant squared, if you notice, I did this as a tabular method. So I set u equal to x, x1, 0, secant squared, integrate, integrate, multiply, multiply, and that's how I got choice E. So what it did is by knowing this tabular method, it honestly simplified a lot of the algebra and what we had to write down. So it's very, very helpful. At the same time, it's very, very hard to do a problem like this with the tabular method. I say hard to do, not impossible to do, but that's because once you understand how and why the tabular method works, you can actually see the mechanics of it a little bit more. So on to 7.5. 7.5, kind of like a preface to this, is what happens if we have like the integral of 1 over x plus 3. We know that this is natural log of the absolute value of x plus 3. What happens if I have 1 over x squared plus 6x plus 9? Well, that is basically saying the integral of x plus 3 to the negative second. And what we could do that is by a power rule and chain. We've already done a few problems like that. Well, what happens now if I want to take the integral of 1 over x squared plus 6x plus 10? If you remember in last time's notes, what we did was we broke that down into 1 over x squared plus 6x plus 9 and then plus 1. So this turns into an arctangent style problem. Now we're going to deal with what happens if we have 1 over x squared plus 6x plus 8. So if we tried to do this as an arctangent, that plus would now become a minus 1, not the happiest thing. So what we would do with this is we would factor this into x plus 4 and x plus 2. By factoring in x plus 4 and x plus 2, what we want to do with that is do the reverse of simplifying that we preach so much in pre-calculus and algebra 2. And what we want to do is break it up into some number over x plus 4 plus some number, I'm going to call b, over x plus 2. And this is partial fraction. So it's partial fraction decomposition in its proper name. But partial fractions is how we are going to approach this. Now, if you remember from partial fractions, if our denominator is a linear factor, we have, and this is a linear factor despite the multiplicity here, but if we have linear factors, we have just a constant in the numerator. If we would have quadratic factors, then we would have a linear factor in the numerator. If we have, say, a cubic, I know I don't have that up there. Suppose I have like x cubed plus x in the denominator, and I'm trying to break it down. I am going to break it down into something over x, then something over x squared plus 1. This had, I probably shouldn't have used x cubed plus x. But anyway, let's say x cubed plus, I'm trying to think of something on the top of my head and it's not really working well. Anyway, the point I was trying to make is we would have to break this down. If suppose this didn't factor, we'd have to break this down into ax squared plus bx plus c. Basically, the numerator has to be 1 degree less than the denominator. So if you look at example 1 that I have here, example 1, what I did initially was I factored my denominator, so it's 2x plus 1 times 2x minus 1. And so I did what I showed above by saying, since this is linear, I have a constant over that 2x plus 1. I have a constant over the 2x minus 1. And what I was showing here in the pink is, in order to combine these, I'd have to multiply that term by 2x minus 1 over 2x minus 1, and this one by 2x plus 1 over 2x plus 1. In doing so, it creates this situation over that common denominator of 2x plus 1, 2x minus 1. So what do I care about when it comes to partial fractions? What I care about more is those numerators are going to be equal to each other. And that's my initial setup. Now, there are two distinct approaches that you could take from here. The system of equations approach is going to be the lesser used one, which is why I'm going to say it first. Because this lesser used one, what we do is we distribute, and then we say, okay, 2a plus 2b is the coefficient in front of x. So that coefficient has to equal 0 because that's the coefficient of the other problem. And then these are the constants, and those constants have to equal 1. So by doing this approach, we now create the system of equations that we could go ahead and solve. Now, the faster approach is more the elimination approach. And what we're saying with the elimination approach, let me change colors here, that if x equals 1/2, which seems like an entirely random number, the reason why I chose 1/2 is because I'm going to eliminate the a. By eliminating the a, what that allows me to do is to say, okay, directly, and I know b is going to 2b equals 1, so b is 1/2. Similarly, at this point, we now go to the other factor and say, what eliminates the other factor? And to eliminate the other factor, we need to say, change color one more time. Let's go, it's a little too close, but oh well. X is -1/2, and by doing that, I can very quickly and efficiently find A. So the moment I have that, you can see that A is that -1/2, and B I did in purple. So that B I did in purple, which is a positive 1/2. Both of those integrate into the natural log function. The reason why, don't forget that this is a 4, is because we have to compensate for that chain of 2 by multiplying by 1/2. And now it's important that we combine these together. So if you notice, I have something on here that I left here that a lot of times we will combine them into one natural log, but you have to be careful. We cannot put the 4th root of that expression there because this is actually a domain change. Now, if I have the absolute values there, I could take the 4th root of it, but it's not very common to actually write it because the whole point of logarithms is to make some of these expressions a little simpler. This is a simpler expression in my mind. Moving right along. This problem right here, if you notice, my numerator is 1 degree above the denominator, which prompts me to have to do some long division. So don't forget some of the other random math skills. How many times does x cubed plus x minus 2 go into this expression? X minus 1 times with the remainder of 2x plus 1 left over. And it is now with this expression that I can do my partial fraction decomposition, which is what I have over here. So if you notice, I did the elimination method. When x equals 1, I get 0a equals 3b, which equals 2 times 1 plus 1. So I'm able to get b quickly and a quickly. B and a are both 1, so I break it apart into those fractions. And as you see, I have combined my natural logs together. Now, if you're an astute student, which I really, really hope you are, you would have noticed, wait a second, I don't feel like we had to do the partial decomposition or partial fraction decomposition. And you're actually right. This is a du over u mentality. So this immediately would integrate into 1/2 x squared minus x plus natural log of the absolute value of the denominator. What I like to show here is why these are equivalent to each other. So it's very, very cool. We have multiple tools that we could use to actually solve our equation. So remember, you're not required to do things one way, but you might need to use a certain approach for a certain type of problem. Example number 3, we have 3 factors. So since we have 3 factors, I now am going to have 3 denominators, which prompts me to have both an A, B, and a C. So what I did was I kind of said, okay, A would have to be multiplied by the other 2, B multiplied by the other 2, C multiplied by the other 2. And then I eliminated what happens if x is 0, my B and my C are gone. If x is -2, my A and my B are gone. So my A and my C are gone. And then if I plug in 2, then A and B are both gone. So basically I could solve for A, B, and C. Now I could write it as my 3 separate fractions, which all turn into very, very quick integrals. and then I wrote it as one common expression down here. Moving right along. Example number 4. This is our first example where, okay, this is x minus 1 squared. Since this is x minus 1 squared, honestly, we could do this as a u equals x minus 1, do a resubstitution, and we could do that problem that way. Nothing wrong with that approach. If we want to do this as a partial fraction decomposition, what we have to do is we have to have, these are both linear factors, even though the multiplicity is 2. So therefore, a over the first plus b over the second. If you see, I did the work to determine what a and b are. And now I have this integral expression, which it looks like I didn't actually complete. So let me go ahead and complete that for you. So this integrates into x minus 1 to the negative first power with the chain, becomes 1 over x minus 1, and then 3 natural log of the absolute value of x minus 1 plus c. Now I put an example number 5 on here because I wanted to show an example of what happens if we have a quadratic factor in the denominator. So by having a quadratic factor in the denominator, what that forced me to have here is this linear numerator. By having this linear numerator, excuse me, then I do still say ax plus b times x equals x plus 2 plus c times x squared plus 1. Basically, you're multiplying by the denominators again. Now, this is a case where I did more of the substitution approach, where c is the only constant, so c has to be 2, and b is the only linear term, so b has to be 1. So I get those immediately. And then this mixture of ax squared and cx squared means if I add a and c, since I have 0x squared here, that has to be 0. And since I already know c, that tells me what a is. So from here, once I know my a, b, and c, I can write it this way. And if you notice, I broke this up into 2 separate fractions. This negative 2x over the first plus 1 over the second. And by doing that, then I end up with 3 separate terms. So the first one is a natural log integration. The second one is arctangent integration. The third is also a natural log integration, which I combine like so. So in the future, I'm going to have to put this in my notes. And then we have some APE problems. So when it comes to our AP problems, what we have to work with is just break it apart using our partial fraction decomposition. Now, one of the things just be careful of is this is the result that I got from my partial fractions. We have to make sure that we can put it together into the answer that we're looking for. Now for problem number 2 here, this problem involved a definite integral. So once I got to the natural log of this, plugging in 3 and 2, this means that yes, we are going to have to understand properties of logarithms for us to be able to come up with our correct answer. Moving right along. For example number 5. Example number 5, this is something in chapter, if you notice my note here, in chapter 5, we're going to show you how this is a logistic differential equation. So this logistic differential equation, right now I'm teaching the mechanics of this. So that's one of the reasons why I like to do this before chapter 5, because then we get into the mechanics of how this differential equation works instead of saying, oh, by the way, this is logistic and you need to know it. So what I did was I factored out a 1 over 400, and then I ended up solving this, and we'll know this a little bit more when we get to our differential equations. I separated my dy and my dx, which means I put all the y's together on this side, and then I'm integrating. And by the way, this y prime is dy dx. So by integrating, I did my partial fraction decomposition to get to this step, and that would be the work for it. Hopefully you can still follow that. This integrates into this expression. Combine our logarithms together. Take e to both sides. Now e to the x plus c1, we could rewrite as c times e to the x, and that's because this is e to the x times e to the c1. So anyway, c e to the x is how we typically write it. Multiply both sides by the 400 minus y. and then distribute, and then bring the y's to the same side and factor it out, and then solve for y. If you notice, this turns into what's known as our logistic form, where 400 is the maximum capacity. So something to keep in mind for the future. 400 is the maximum capacity. And then the rate is involved in that exponent right there. But we'll get into that more as we get into our chapter 5 problems. So I wish you guys the best and good luck to you.